Ever tried solving a puzzle where the rules themselves were so complicated, they made the puzzle impossible? That's essentially what happens when we encode complex problems like graph theory or scheduling into conjunctive normal form, CNF, a format that's critical for solving logic-based problems. These encodings act like the rules of the puzzle, and if they're too messy, even the smartest computers struggle to find a solution. But here's the breakthrough. Researchers just found a way to simplify these rules dramatically. Imagine shrinking a giant maze into a tiny map. This technique cuts the number of rules needed for certain problems from billions to millions. Let's dive into how it works. Let's start with the basics. In graph problems, like finding an independent set, a group of nodes with no connections between them, traditional methods force computers to write every single rule about which nodes can't coexist. For a dense graph, where almost every node connects to every other, that's like writing a rule for every possible pair. The result? A massive list of constraints, or clauses, that grows quadratically with the number of nodes. But what if we could group those rules smarter? Enter BICLIQUE coverings, a technique that divides the graph into smaller, structured subgraphs. Think of it like organizing a party. Instead of checking every possible pair of guests to avoid conflicts, you split them into groups where conflicts are already managed. This reduces the number of rules needed because each group's constraints are handled once, not repeatedly. The key insight here is that even in a superdense graph, there's hidden structure you can exploit. Research shows that any graph with enough edges must contain a BICLIQUE, two groups of nodes where every node in one connects to every node in the other. By targeting these BICLIQUEs, the new method cuts the number of clauses from OV2 to OV2 log V. It's like replacing a highway with a shortcut. The distance is still there, but the journey is way smoother. And it's not just theory. This approach has already simplified real-world problems. For example, in string compression, it reduced the complexity of encoding constraints, and in scheduling, it transformed a seemingly intractable problem into one a computer can solve in seconds. But let's pivot to another challenge, non-preemptive scheduling, where tasks on machines can't be interrupted. The old way of encoding this. It was like solving a Rubik's Cube by randomly twisting each face. You'd need thousands of rules to cover every possible overlap between tasks, and the complexity scaled as omega T4, which means it's way too slow for real-world use. Here's where the interval propagation trick shines. Instead of checking every possible overlap, researchers broke the problem into smaller blocks. Within each block, they used special variables to track whether tasks fit without conflicts. It's like having a checklist for each section of a puzzle. Does this piece go here? No. Move to the next one. This slashed the number of rules from thousands to just a fraction of that. The math tells the story. For a factory with T tasks, the old method scaled as T4, 10 tasks equals 10,000 rules, 20 tasks equals 160,000 rules. The new method, OT3 log T, so 20 tasks now need around 8,000 rules. It's not just faster, it's orders of magnitude more efficient. Why does this matter? Because these optimizations underpin modern tech. Think of logistics companies planning delivery routes or cloud servers managing millions of user requests. Every time you stream a video or get GPS navigation, you're benefiting from these smart algorithms. The interval propagation trick isn't just a theoretical win, it's a practical game changer. The takeaway: when faced with a huge, complicated problem, the key isn't brute force. It's about breaking it into smaller, smarter pieces. Whether it's scheduling tasks, compressing data, or solving puzzles, the most powerful solutions often come from rethinking how we frame the problem. So next time you're stuck on a tricky challenge, remember, sometimes the answer isn't in the complexity, it's in the structure. Thanks for watching. Stay curious, and we'll see you next time.